So this is continuing chapter 16. For this initial discussion, you're going to need a calculator for this. So I'm going to run through a practice problem or two to kind of give you some pointers on how to do pH calculations. So if you're given an H plus or hydronium ion concentration of 1.2 times 10 to the negative fourth molarity, find the POH and the OH ion hydroxide ion concentration for this. So I'm going to pause the video and come back with the answer, so try it on your own. So for this calculation or set of calculations you're going to be asked to do, you could approach them two different ways. So one, you could always take the hydrogen ion concentration and divide it into 1 times 10 to the negative 14 to find your hydroxide concentration, and then take the negative log of that to find your POH. So this is your POH. The other way you can do these problems, and again, it's a personal preference, I could take the negative log of this number to find the pH. So if I take the negative log of 1.2 times the negative fourth, I get 3.92. So if I subtract that from 14, I get my POH here as well. Now, how do I find the hydroxide concentration once I have my POH? Well, if I take 10 to the negative, so if you look on your calculator, if you look above your log button, you're going to see it's a 10x function. So if you put 10 minus the POH or 10 minus the pH, you will get the hydrogen ion concentration or the hydroxide concentration, depending upon what you're looking at. So you could do it either way. You will get pretty much the same answer. You might have some rounding issues here or there, but that's going to be how you approach those problems. Now, second thing I want to talk about is sig figs for pH. You essentially have two sig figs given in this problem, okay? Because you have 1.2 times 10 to the negative fourth. So your answer must have 2 digits after the decimal for your sig figs. That's because the scale is based off of 0 to 14. So that first number in front of the decimal is going to be anywhere between 1 and 14. So you can't use that for sig figs necessarily because that's the scale it's based off of. So it's digits after the decimal for your pH and your POH calculation. All right, so the second problem I'm going to do before we get to strong and weaks is this one. And this one is kind of looking a little further ahead at some of the concepts we're talking about. What is the pH of a solution obtained by reacting 0.2 moles of sodium solid with 500 mils of water? So this kind of incorporates a couple different things all in once. So again, there used to be more of an emphasis on the actual equations. So here's the equation. Sodium solid goes into liquid water to produce sodium hydroxide and hydrogen gas. This isn't balanced, so I need a 2 in front of the Na, a 2 in front of the water, and the 2 in front of the NaOH. Now it is balanced. But really what we care about in acid-base chemistry is the NaOH in aqueous system. So really what's floating around in that beaker, and we're going to talk more about this in a second, is I have Na plus and OH minus. What I care about is that OH minus, okay? That's going to tell me what my pH is. So going back to the problem, I was given 0.2 moles of sodium solid and 500 mils of water, so I could find a concentration of that. So I could take 0.2 moles and divide it by 0.5 liters, and I'm going to get 0.4 molarity. So do note that that is going to be essentially the molarity of this aqueous solution, okay? So that's going to be the concentration of the OH. So back to when we were talking about solutions, whatever the bottle says, that's how much you have of each one of those ions floating around. So if that's the case, that's my OH concentration. If I take the negative log of 0.4, I'm going to get my POH to be 0.4. So if I subtract 14 minus 0.4, I get 13.6 as my pH, which is expected because, again, I make the sodium hydroxide. That's going to be a strong base. Okay, so this is what we call a strong base. That doesn't mean the concentration is strong or anything like that. It just has to do with its association. So that is going to be your final answer, is the 13.6. So I mentioned the word strong. So let's talk about strong versus weak. Okay, and we mentioned this first semester a little bit. So this is where you're going to have to know in depth what we're talking about here. All right, so strong acids are things that completely dissociate or completely ionize in water. okay? So what I want you to focus on is HCl is a strong acid, and I want you to focus on the arrows. The arrow is going to be very important for our discussions here. So what I'm saying is HCl is a strong acid. It completely breaks up into H plus and Cl minus. So what does that look like in the beaker? Okay, so please draw a beaker over on the side, and I'm putting HCl into a beaker of water, Well, what's the predominant thing or species in that beaker? Well, of course, it's going to be water. Okay, no matter what I dump in there, the water is going to be the biggest thing that you have in there. So what do you have floating around once you have dumped the HCl in there? Well, you have produced hydronium ion and chloride ion. So again, please know hydronium ion and H plus are going to be interchangeable in the world of chemistry. So I don't care how you write it, but the more correct way is to write hydronium ion. You will not find any HCl in there as a complete molecule, okay? So that's what it means to completely dissociate. So going back to our discussion of concentration, so when we are doing strong acids, if I have a 0.1 molar bottle of hydrochloric acid from the stockroom, what does that tell me about the concentration of those ions? Well, it's exactly 0.1 and 0.1 for each one of those. I will be just as likely to find the hydronium ion as I am the chloride ion. So if I want the if I want to know the pH of my strong acid, all I got to do is take the negative log of my concentration, and I will then find my pH. Okay. So strong acids are very easy for pH calculations. Now here are the strong acids. Now please note this last one is not considered a strong acid. So it's just the first 6 in this list, but sometimes you will see that HClO3 is sometimes listed as a strong acid. But on my test and on the AP test, those are going to be your strong acids. Those are going to be your strong acids. So what does it mean to be weak then? Well, weak means it does not completely dissociate, okay? That's the definition of a weak. So it doesn't have to do with concentration, so please do not misinterpret that. So a weak acid is going to have a Ka. It's going to have that dissociation constant that I mentioned before. So the weaker the acid, the smaller the Ka is going to be. So we have an equilibrium problem that we're talking about, okay? So we're going to have a double-headed arrow that we are going to be looking at. So the most common weak acid that we see is acetic acid, okay? So let's say I have acetic acid being dumped into a beaker of water. What is that going to look like? How does that look different than a strong? So again, water is the predominant species in there. But with this equation, so I'm going to write it on the bottom here. Again, please keep in mind that it is a double-headed arrow, I get acetate ion and hydronium ion. So because this is only partially, does not completely dissociate, okay, I want you to draw relatively big, the complete molecule of acetic acid, relatively big. Then I have some of those ions in there. So I always do something goofy. I always go, you got tiny, tiny, little, tiny H3O plus and tiny, tiny, little, tiny, tiny, little acetate, okay, in comparison to the overall acid. So that is what makes weak acids much different. So because these are equilibrium systems, I have to do an equilibrium problem to see how much I have of the H3O plus in there versus what I started with. So I can't just look at the concentration and be done. The other thing that we will be doing with the calculations is something called a percent dissociation, okay? And that is the amount that breaks up over the initial concentration. And it's going to be a very small number, usually less than 5% for what we're looking at. Now, to kind of finish this up, realize that because you have a large amount of H3O plus in here, your pH for your strong acids are going to be usually less than 1 or around 1 because of the fact that strong acids, even if you have just very small concentration, you're going to have a very huge amount of H3O plus being produced there. While if you are looking at H3O plus in a weak acid, your pHs are going to be much bigger, meaning you're going to be in the 2 to 3 to 4 range, depending upon the concentration. So that is, you do see a difference in pH if we're talking the same concentration with strong versus weak, due to the fact that weaks only partially, do not completely dissociate.